Hello, and welcome to my talk on the shape of dendritic tips. My name is Andrew Coe from the University of Greenwich. I'd also like to acknowledge my co-authors, Lioba Toropova, Dmitry Alexandrov, and Peter Galenko. Today I'm going to talk about tip shapes and some of the background theories, including the Ivantsov, Brenner, Plapp and Karma solutions. And then I'm going to talk about a generalized form developed by Alexandrov and Galenko. And then I'm going to compare this new AG theory to numerical modeling results from the enthalpy method and the phase field method, and then also to some experimental data looking at ice dendrites and succinyl nitrile. And then I will conclude. The tip shape has been investigated for many years now, beginning with the Ivantsov solution from going back to 1947, where he looked at steady state growth of a parabola in 2D and a paraboloid in 3D, and showed that through the Ivantsov solution that it goes generally as x squared. Then in 1993, along came Brenner, who, using a timescale from Almgren, showed that in 2D that the tip takes the form of x to the 5th over 3. And then in 2000, Plapp and Karma then showed, using a computational multiscale random walk, that the scaling law must be changed for 3D, and so for an axis symmetric dendrite becomes x to the 3 over 2. Now the Ivantsov solution works well in the vicinity of the tip, but the Brenner and Plapp and Karma solutions, which have been shown experimentally to capture the dendrite shape very well, but apply more to regions far away from the tip. And so the Alexandrov-Galenko generalized theory essentially combines the short length scale of the Ivantsov solution with the larger length scales of the Brenner and Plapp and Karma solutions. And so for a 2D dendrite tip, it is given in this form, where you have these two functions, bs and bl, which are stitching functions that follow asymptotic conditions. And Alexandrov and Galenko chose these to be of the form here, which is the exponentials to minus 1 over x to the power of 2k, and bl to be exponential to minus x squared times k. And the condition is that as bs goes to 0, bl goes to 1 in the vicinity of the tip, i.e. when x goes to 0. And if we apply this to this general form at the top, we can see that the bs terms disappear or vanish, leaving just bl, which tends to 1 and ultimately tends to the Ivantsov solution. Conversely, as x becomes much greater than 1, bs tends to 1 and bl tends to 0. And so applying that again to the generalized solution, bl vanishes, and so we end up with this term here, where bs tends to 1, and then this conforms to x to the 5th over 3, which is the Brenner solution. And so then in 3D we have a slightly different generalized form, which is given here, where the only difference between this and 2D is that some of the exponents have changed to account for the difference in the Plapp and Karma and Brenner solutions. We have the same stitching functions, and so applying these asymptotic limits, again we see that as bs goes to 0 and bl goes to 1 in the vicinity of the tip as x goes to 0, that the Alexandrov-Galenko theory conforms to the Ivantsov solution. And conversely, as bs goes to 1 and bl goes to 0 for x much greater than 1, then the Alexandrov-Galenko theory conforms to the Plapp and Karma solution. And so we can actually combine both the 2D and 3D solutions into a single form given here, where n represents the number of dimensions, so 2 and 3 for 2 and 3D respectively. So looking at the behavior of these various solutions, on the left-hand side here, when x is small, so the limits here are between minus 1 and 1, so this is in the vicinity of the tip, we have this blue line which represents the Ivantsov solution, and we can see that the Alexandrov Alexandrov-Galenko theory matches that very well, whereas the red line is the Brenner solution. Moving to the larger length scale, however, where x is now in the region of 4 and -4, we can see that the Ivansov solution given here by the blue line doesn't match very well with the Brenner solution given by the red line, but the Alexandrov-Galenko solution does. And so then you have this intermediate region where there's a transition between the Ivansov solution and the Brenner solution, and you can see the green dots here represent the Alexandrov-Galenko solution, and this is for a value of k, which feeds into those stitching functions. And so k essentially determines how smooth the transition you have between the Ivansov and Brenner solution. In 3D, we see a similar behavior. So again, the blue line here is the Ivansov solution, and the red here is the Plapp-Karma solution now. And again, the green dots are the Alexandrov-Galenko solution. And so the generalized theory provides a smooth transition between essentially two theories, that one that works in the short range and one that works in the larger length scale. One of the methods we have used to compare the dendrite tip shape to is the enthalpy method. Normally, we have used this on large-scale problems. An example here is surface patterning and powder atomization. But we've also found that it works very well at the smaller length scales looking at the dendrite tip. And so, for example, in a recent paper that we published in the Journal of Physics Condensed Matter, we were analyzing the tip velocity and tip radius as a function of undercooling, and we found that the enthalpy method was able to provide an excellent match to sharp interface models. But we can also get increasing detail from this. The model itself is predicting the actual morphology of the dendrite tip, as well as aspects such as the thermal boundary layer. And so on the left here you can see the simulation domain, and the inset you can see the dendrite tip morphology as well as the undercooling at the tip. On the right hand side you can see the comparison to the Alexandrov-Galenko generalized tip shape model, and this was applied to pure nickel. We also used a phase field method, which is traditionally shown to be an accurate predictor of dendrite tip behavior. So on the left hand side here we have numerical calculations of an ice crystal, and this was shown to match extremely well with again the sharp interface model for both tip velocity and the tip radius. And we calibrated this model to again look at pure nickel, and so again on the right hand side you can see here an excellent match to the Alexandrov-Galenko theory for tip shapes. Looking into the experimental region, we have collated data from across the literature. So we have data here from Shibkov and Yokoyama and Yoshikaze, all looking at ice dendrite experiments. And in each case, you can see from the images and then the corresponding data that's been extracted, and then the generalized Alexandrov-Galenko solution, that it matches very well both in the region of the tip and also further away. And then finally, we looked at experiments for sintonitrile experiments. So here's data from Huang and Glicksman, and we have Ramirez and Huang and Wang, again spanning experiments that have been conducted over the last 30 years. And what we can see, again, from extracting the data from the tip shapes and the images captured, we see an excellent match to the Alexandrov-Galenko theory. So to conclude, here we've shown a generalized form for dendritic tip shape, which was derived through the use of stitching functions that provide a smooth transition from near the tip, where we have the Evans-Solve solution to the larger length scales where we have Brenner and the Allam, Karma, and Plapp solutions. Um, I then showed that this solution, the Alexandrov-Galenko solution or theory, has an excellent agreement when compared to both numerical simulations using the enthalpy method and the phase field method for pure nickel, and also agrees extremely well with experimental results for ice dendrites and for experimental results of synctyl nitrile. Going on into further work, we aim to investigate numerically and capture for various Peclet numbers growth that leads to tips with isotropic globe-like structures and anisotropic globe, and also angled dendrites at the higher Peclet numbers, the influence of solute, and the influence of fluid flow. And with that, I would like to say thank you for your time, and I hope you enjoyed the presentation.